Hello everyone, welcome back to another video for the series. I'm Inokyu and today I brought a very interesting problem from Finland. And the reason why this problem is really interesting is because this is actually the exact same thing as a very renowned theorem in geometry called butterfly theorem, and this problem just told us to prove this theorem. And yeah, so it's my first time seeing a very famous theorem as a problem in an Olympiad or competition, so I loved it. Yeah, but please watch this video till the end, because I think I know that most of the people who are watching this video or who studied Olympiad already knows how to prove this theorem. However, I'm going to prove it in a different way too. Like, I'm going to prove it in two different ways. I will explain it while drawing the diagram because it takes a while to draw them. So I think many of you might know the proof using similar triangles. So that's what I'm going to do right now. I'm going to prove it using similar triangles and power of a point theorem. But I'm also going to prove it using the projective geometry. Oops. And projective geometry is actually quite interesting. Using cross ratios to prove this is actually quite interesting. So please watch the video till the end. And the reason why this is called butterfly theorem, I think, is because our diagram actually looks like a butterfly if we finish drawing it. So we have let's just go like this: B, C, D, P, Q, M. So what this is saying is, if M is the midpoint of PQ, then it is also the midpoint of XY. So if M is the midpoint of PQ, it is also the midpoint of XY. Okay, so let's start our proof. Our first proof uses a similar triangle, as mentioned. So before using similar triangles, we actually need to draw a few additional lines. Here to here, and here to here. We can actually notice a few similar triangles here. So this is an 90 degrees. This is 90 degrees. This is also 90 degrees. This is 90 degrees, and this is also 90 degrees. Let's call this x sub 1, y sub 1, x sub 2, and y sub 2. Because it's AB and CD, and AB comes first. Yeah, and right now let's define the other few lengths. Let's call this x. Sorry, let's call this y. Let's call this half a, and obviously the other half would also be a. Okay, so let's take a look at the similar triangles. So we know that these I'm sorry. Is it marker? Yeah. I think I'll just quickly use the highlighters to share which triangles are similar to each other. So this triangle and this triangle, they're similar by AA similarity because one is 90 degrees and they share these two angles are the same, and this one and this one, they're also similar in similar fashion, and we have two more. So this one, this, and this, they are similar, and the last one is this one and this one. Should we take a look at the yellow ones first? So let's take a look at yellow one. I will just represent it like this. Yeah, I'm not sure if that's a great idea. No, sorry. I'll represent yellow like this. Okay, so yellow one tells us that x to y equals x sub 2 to y sub 1. This is equal to sorry, I'm allergic to seasons and can't really focus right now. Sorry. Yeah, we know that x to y equals x y sub 2 to y sub 1. It's also equal to x sub 2m to my sub 2. Okay, now next one. Let's look at the pink one. The pink one tells us that x to y equals x sub 1 to y sub y sub 1? No, y sub 2. Y sub 1. X sub 2. Sorry, yeah, x sub 2, y sub 2. I accidentally. This equals x sub 1m to y sub 1. And now the next one is this color. It tells us that x sub 2 to y sub 1 equals dx to bq, and this is equal to dx sub 2 to by sub 1. And the next one is ax sub 1 x sub 1 to y sub 2 equals ax to cq, and this is equal to ax sub 1 to cy sub 2. Now let's take a look at the ratios and see which ones would actually help us prove the theorem. Ax sub 1, cy sub 2, I'm not sure if that would be that helpful. Might be, but not really. Because we have too many ratios right now, we kind of want to like organize them and only focus on the important ones. Next one is dy sub 2. How can we get dy sub 2? Qy sub 2. I'm sorry, it's qy sub 2. Qy sub 2 to by sub 1. Wait. No, it's actually d. It's not y. It's x. This to that. I'm not sure if those will help a lot. X sub 1 to my sub 1. Maybe, but these two are more significant because x and y, we know that they are significant, and these two are important because it helps us to kind of relate with these ratios too. So let's scratch these two out. So let's only focus on these four ratios. Okay, so we know that x over y equals x sub 2, y sub 2. This equals x sub 1 over y sub 1. And notice that x sub 2 over y sub 1 equals dx over bq. And x sub 1 over y sub 2 equals ax over cq. I just rewrote them. And it's quite natural to try and multiply these two because we know that dx over bq times ax over cq equals x sub 2 y sub 1 times x sub 1 over y sub 2. Let's switch these two, so we have x sub 1 and y sub 1 times x sub 2 y sub 2. Notice that these are all equal to x over y. Therefore, we get x squared over y squared. Now, let's take a look at dx over bq times ax over cq. Dx times ax. This looks quite familiar because it's a power of a point theorem. So dx times ax equals px to xq. bq qc similarly is py and yq. This is equal to x squared over y squared. Should we write these in terms of a and x and y? Okay, so what is px? Px is a minus x. What is xy? I mean xq. Xq is x plus a. We have py equals x plus a plus x. I mean y. And yq equals a minus y. This is equal to a minus y. this is equal to a squared minus x squared over a squared minus y squared. Okay, these are the same. So because we know that they are the same, let's add them. This is equal to x minus x squared. So the property that I'm currently using right now is this one. Because I don't really want to multiply them, and I mean we could do that, but like we have a better way. X squared minus y squared plus y squared, and this is obviously equal to 1. Therefore, x squared over y squared equals 1 and x equals y. So therefore m is the midpoint of xy. We proved it. So this is like the most classic proof, I think, what many other people use. But now I want to introduce a way to prove it using projective geometry. So I'm not sure, but I am planning to make a separate videos about cross ratios and projective geometry because they are quite important in Olympiads. We don't need all that. We don't need this, we don't need. We only need the basic information. No. This one. Oh, this one and why can't I erase it? Wait, is there any way to sorry, I really need to erase this, but oh wait, I found. Wait. Oh wait, this is no good. I need stroke eraser to no. Should I just draw a new line? I don't want to do that. My last chance. Okay. I'll just draw another line. This looks good enough. Yeah. Okay. This is x. This is y. So let's use projective geometry and cross ratios. Okay, first of all, the cross ratio. Okay, so if we have a circle like this, if we have 4 points, the cross ratio of these 4 points equals the cross ratio of these 4 lines. Segments, not lines. And that is, and the cross ratio of these 4 lines is equal to the cross ratios of these 4 points. We're going to use that. That's the basic thing that we're going to do today, use today. So let's pick 4 points. Why don't we choose PACQ? So the cross ratio of PCAQ is equal to the cross ratios of PCAQ. This one. So PDDC. So PDDC. Wait, it's yeah, because this looks quite weird because we usually name all the segments when we write them. But anyways, I think everyone can understand what I'm trying to say here. This segment and DQ. And similarly, when we write that with B, BA, and BQ. Now, let's take a look at this one. PD, DC, PD, DC, this one. The cross ratios of this 4 is equal to the cross ratio of this 4, 1, 2, 3, 4. That is equal to this 4, 1, 2, 3, 4. That is equal to this one. So 1, 2, 3, 4. Nice. So we could actually use the red one. So this one, I'll just move them down here. So this is equal to PM, DA is X, DQ is Q, DC, DA, DQ. So Q. This one is equal to P, BC. What is BC? BC is Y, BA, M, and BQ is Q. Okay, so we know that this is true. Then should we try and rewrite them? Okay, I'm sorry, I'm going to do this one more time. So this ratio is equal to px over mx divided by px mx pq over mq. This is q. So this is equal to px times mq over mx times pq. Similarly, this is equal to pm over ym over ym over yq. PM ym pq over yq. This equals pm times yq over ym times pq. Okay, so we know that these are true. So we know that px times mq over mx times pq equals pm times yq over ym times pq. We have pq here. Let's erase them. How about yq? Px. mp? mb? Is it b? No, it's q. mq equals pm, so we could also erase these two. So what we have is px over mx equals qy over ym. So how should we continue from here? And notice that we could actually do the same thing here. So rewriting, we have px over mx equals yq over ym. This is equal to mx plus ym over px plus yq. What is mx plus ym? Oh wait, no, sorry. No, sorry. Q over ym. Let's call this a and x and y respectively, like just as we did it right here. So what is px? Px is a minus x over x equals to a minus y over y. Therefore, ax minus xy equals ay minus xy, so therefore x equals y. And that completes our proof. Yay! So I think, personally, I prefer the method using cross ratios because it just feels cooler and it's actually more simple. Yeah, not because it looks quite advanced, but just because the proof is shorter. I love shorter proofs. Yeah, so I think this is butterfly theorem, and I also really enjoyed reviewing about similar triangles and also reviewing few of the properties about cross ratios. Thank you so much for watching this video, and tomorrow I'll come back with another very fun and interesting problem. Thank you and see you tomorrow. Bye.